Okay, so welcome to today's lecture recap. We're going to continue on in our discussion of simple harmonic motion, which we understood as a very universal phenomena that happens when you have a physical system and it's in a stable mechanical equilibrium position, and then you displace it from that position a little bit. We have, in that case, the idea of a restoring force. So a force that tends to bring the system back to its equilibrium position. And the action of these restoring forces, if you use Newton's laws, give rise to displacement as a function of time that is a simple periodic function. And so we choose to write that as a cosine. So this function has a number of parameters. And we understood last time that the parameter omega here, that's related directly to the period of the oscillation. So the omega equals 2 pi divided by the period. Okay. And physically speaking, that is determined by the mass and the restoring force, or the constant k that appears in the plot of restoring force versus position. So omega equals the square root of k over m. So given a particular system like this mass on this particular spring, then for all possible oscillations of that system, small oscillations around equilibrium, you're going to find the same period or the same angular frequency. But then you have these other parameters, A and the phase phi, and these ones are determined not by the system itself, but by the initial conditions that you start the oscillation with. So depending on if you displace it to the left or to the right, or perhaps initially don't have any displacement, but you have some initial velocity, the A parameter and the phi parameter are going to be different. Okay. And so we understood that last time the amplitude, or the A parameter, that's just going to be the total amplitude. And so if you're able to observe the motion, then it's quite easy to figure out what the A is just by looking at how far is the displacement from the equilibrium position, or taking the difference between the maximum and minimum positions, that would be twice the amplitude. The phase parameter we understood last time is related to how much is this motion, or the graph of the motion, shifted relative to just a standard cosine function. So a standard cosine function starts at the maximum at time equals 0 and then goes downward. If we look at our particular oscillation, then you can understand that by adding a phase of 2 pi, that would shift our graph to the left by an entire period. Subtracting a phase of 2 pi would shift it to the right by an entire period. And so if you have an example like the one in the picture here, what you want to do is just look at how much the shift is, ask what fraction of a period is that, and then take that same fraction and multiply it by 2 pi. And that will be the magnitude of your phase. Okay, and so shifts to the right, those are negative phases. Shifts to the left, those are positive phases. So we're going to get started then with an example where I tell you the mass on the spring in the picture is initially at its equilibrium position, but it's struck by a hammer, so it has an initial downward velocity. And we want to ask first, what is the motion as a function of time? Which one of these options? And then second, can we determine the amplitude of this motion given the initial velocity v0 and the frequency parameter for this motion omega? Okay, so take a few minutes to think through that, and now I'll discuss how we would approach this question. Okay, so let's draw ourselves a picture here. So what we want to do first is to think about, as a function of time, what is this motion going to look like? So let's consider the upward displacement x as plotted as a function of time. And so what we're told in the problem is that initially the system is at its equilibrium position. And then it goes downward And so that means that we're talking about a sinusoidal oscillation that starts like this, and then it'll come back up, and it'll go down again, and so forth. And the previous times it would have, if it had been going before, it would have looked like this. Okay. But really we're starting at t equals 0. So the first thing we want to do in order to answer this question is basically to figure out the phase. All of these options are the same except for the phase. And so what we're instructed to do is to compare our function with an ordinary cosine function and understand how is it shifted. Okay, so this is a cosine, and so we want to go from the cosine to our function. And what we notice is that it is shifted to the left. Okay, so the maximum of the cosine is here at 0 in the standard cosine. And then in our case, this would be shifted to the left, or the first minimum, the first, 0 of the cosine is there, but in our case, that's right at time equals 0. So it's shifted to the left, and it's shifted to the left by an amount which is a quarter period. Okay, so because the distance from the maximum to the 0 is 1/4 of the entire period. So 1, 2, 3, 4. Okay, and so that means that phi is equal to, and so we are shifted to the left, so it's going to be a positive phase. And then we basically take 2 pi and multiply it by 1/4. And so that's equal to pi over 2. Okay, so that's telling us that the answer for this question, the answer for this question is going to be C. I can't grab it. So C is A cos omega t plus pi over 2. And now we can consider the extra part of this question, which is, can we determine the amplitude given this initial downward velocity of magnitude v0 and given the frequency, the angular frequency omega? So this is our next question. What is A? We're given v0 and omega. And so to answer this question, what we want to do is understand first, what is the velocity as a function of time? So in order to relate things to this velocity parameter, we'll want to know what is the velocity as a function of time given this graph, or given this function for the position. So to figure out the velocity from the displacement, we just need to take a derivative. And so using the chain rule, that gives us minus a times sine of omega t plus phi over 2. And then differentiating the inside gives us an extra factor of omega. And so altogether, we have minus a omega times sine of omega t plus pi over 2. Okay, now we're in good shape because we can say that for time equals 0, then this gives us v is equal to minus a times omega. And then plugging t equals 0 into the sine gives us sine of pi over 2, which is equal to 1. Okay, so I can write that out. And we're told that this is equal to v minus v0. And so that then allows us to figure out the amplitude, just solving there. And that would be equal to v0 over omega. Okay, so that's the extra part. So let's get right into another question. This is the theme today, basically understanding relations between velocities and displacement and later acceleration. And so let's just get right into another question using the same kind of ideas. And here we're given the position as a function of time for a specific oscillation. And what we want to know is, what is the velocity as a function of time for the same motion? Okay, so pause your video, think about that. And now we will discuss it. Let me use the back side of the paper here. All right, so here's the graph of position versus time. It actually looks like a standard kind of cosine function, no phase shift in this case. And we want to know what the velocity as a function of time is. And so the key here is that the velocity as a function of time is just the derivative. So we could try to write down the mathematical function and then take the derivative. But instead, what we can do is actually understand everything just based on the graphs. So this is the key step, is to understand that this derivative is the slope of the x versus time graph. And so if we want to plot the velocity as a function of time, then that is basically just plotting the slope of this graph as a function of time. And so we don't really need to know the values. We could basically just answer this question by understanding where is the slope 0 or positive or negative. And so we see that at time equals 0, the position graph has 0 slope. And then after time equals 0, the slope becomes negative. At this point here, the slope is some maximum negative value before going back to 0 at the middle point of this graph. And then the slope becomes positive, reaches some maximum value, and then finally is 0 again. And so our slope versus time graph, which is the velocity, looks like this one. Okay. And so we can see that in this case, the answer is E. So just to summarize that then, what we understood is that the velocity of our motion, and this applies not just to simple harmonic motion, but to any kind of motion, the velocity is the derivative of position, and the velocity versus time graph is then just a graph of the slope of the position versus time graph. So it happens in this case that the velocity versus time graph in whatever units we're using here has the same amplitude as the position versus time graph. But that's kind of just a coincidence, or it happens that in these units that whatever, they're not even specified, but in whatever units we're using here, then omega is equal to 1 because you see the period is 2 pi. And so then when you take the derivative of the position graph, you get an extra factor of omega out, but that's equal to 1. And so it looks like then the amplitude for the velocity graph is the same as the amplitude for the position graph in these units. But generally, we're going to find that those will be scaled relative to each other. So if the position graph has amplitude 1, then the velocity graph would have amplitude omega because of that extra factor of omega that comes out when you take the derivative. Okay, so that's this factor right here. Okay, so this is sort of a more general situation where you'd have amplitude A for position. The amplitude of velocity would be omega times A, and the amplitude for acceleration would be omega squared times A. So let's have one more question about velocity before we consider some questions related to acceleration. So in this case, we're asking, given the graph of position versus time again, how can we figure out what the maximum velocity for this simple harmonic oscillation is? And by the way, there's a little bit of an error. This should actually go down to -2. I didn't mean for the amplitude to be changing. Okay, so think about that a little bit, and then we'll go through it. So let's have a look. We have x of t. It's given by some kind of simple harmonic motion, so for some amplitude and some phase. And we're trying to figure out what is the maximum magnitude of velocity. And so again, it'll be useful for us to remember that the velocity is the derivative of this, which is a cos omega t plus phi. And so the maximum magnitude of velocity that's going to be given by the amplitude times omega. Okay, so again, because this should be a sine, because the sine function only goes between -1 and 1, and so that will be maximum when we just set the sine equal to 1, and then the velocity is equal to plus or minus a omega, and so the maximum magnitude of velocity is a times omega. And so now from the graph, we see that the amplitude here is 2 centimeters. And then we want to figure out what is omega. And so here we can use the relation between omega and the period. So omega equals 2 pi over t. What is the period of this graph? Well, it's a little bit tricky because the graph doesn't even show an entire period of this cosine function. So what we can read off the graph most easily is 1/2 of a period. So going from the maximum to the minimum, that's 1/2 of the period. And so that is 9 pi over 2 minus pi over 2, which is equal to 4 pi. And so we learn that t is equal to 8 pi for this oscillation. And then that implies that omega equals 1/4. And so V max equals A times omega, which is equal to 2 centimeters times 1/4. This should be seconds inverse. And so that's 1/2 centimeter per second. Okay, so the answer for that one is D. Okay, so moving on, let's consider this question about acceleration. And so the question gives you, again, well, in this case, it's the acceleration versus time graph. So here we're trying to go backwards. We have the acceleration versus time graph, and we want to understand the position versus time graph. So take a minute to try to think about how will we do that. Okay, so there's actually a couple of ways that we can understand this question. So I'll tell you both of them. So one way to think about this question would be this idea that the acceleration is the slope of the velocity graph and the velocity is the slope of the position graph. And so then we could try to figure out, well, what would velocity look like? You know, what function would have this graph as its slope? And then we could understand what would position look like, which is what function would have that velocity graph as its slope. But there's a slightly simpler way to understand the answer to this question. And so that is to use the relation in simple harmonic motion that acceleration equals, remember, it's F over m from Newton's second law, but it's equal to then minus k over m times x using the form of the restoring force. And so that would equal, and that's equal to minus omega squared x. Okay, so in this case, this is actually going to be the simplest way to answer this question, because what it shows us is that acceleration and position are just related by flipping the sign and then multiplying by omega squared. In this case, again, omega is just equal to 1. And so what we expect is that the acceleration versus time graph and the position versus time graph are just the negative of each other. And so we can then understand directly, without further calculations, that the answer to this question is D. So D would be the position versus time graph. And we could also check, starting from D, we could take the derivative and or look at the slope versus time of that to get the velocity, look at the slope of the velocity versus time to get the acceleration, and we would find that going from here as position, we would end up with this one as acceleration. Okay. One more graph, one more acceleration question here. Okay. So in this graph, what we're given is on the left, the acceleration versus time for one object. And on the right, we're given acceleration versus time for a different object. And we see that the amplitudes are the same for acceleration, but apparently the frequency is different, because in this case, it takes time 6 to do one entire period. In this case, it takes time 3 to go through an entire period. And what we're asked is, how would we relate the amplitude of displacement for the first one versus the second one? So I want you to think about that for a little bit and see if you can come up with the answer. Okay, so to answer this question, actually, the formula that we need is the one that we just had on the paper already. Okay, so acceleration equals minus omega squared times x. So if we want to understand displacement or position, then we could say x equals minus a over omega squared. And so now comparing these two graphs, for the second oscillator, what we see is that the period is equal to 1/2 of the period of the first oscillator. And so the frequency is going to be, because that's inversely related to the period, that's going to be double the frequency of the first oscillation, double the frequency of the first oscillator. Okay. And so now we can say that the amplitude for x, so looking at this formula here, what you see is that the amplitude for position is going to be related to the amplitude for acceleration divided by omega squared. Okay, and so because the second one has twice the omega, then the amplitude for position is going to be 1/4 the amplitude for acceleration in these units. Okay. And so if the amplitude for the displacement in the first case is 1 centimeter, then what we would conclude is that the amplitude for the displacement, in the second case must be 1/4 of a centimeter. Okay, so just maybe going through that one more time, we have that the acceleration is minus omega squared x. So x equals minus a over omega squared. The period is 1/2 in the second case, so omega is double. And so that means that the amplitude of x in the second case will be 1/4 of the amplitude for x in the first case. Okay, so this next question asks us to figure out the spring constant for a particular oscillation that I'm going to show you in a video. So let's actually pull up the video here. So we're going to watch the video and then try to figure out what is the spring constant for the mass on the spring system that we're going to watch in the video? Okay, so we're putting a mass on the spring. It looks like it's 250 grams. Okay, and it's oscillating up and down. Okay, so let's talk through how are we going to figure out the spring constant K. And so I will set my camera up here. So our first thought should be, well, what is it that the spring constant affects? Okay. So if we think about our formulas for simple harmonic motion, we know that the spring constant comes in our formula for omega. Okay, so that would be one formula. The other formula that we have where the spring constant shows up is the formula for the restoring force itself. So if we could figure out what the force on this object is and the displacement, oops, let me go back. Okay, so we'll replay that one. We could figure out what K is, but we can't really figure out the force because this is not just the force of gravity. This is the net force on our object. Okay, and so knowing the net force requires us to know something about the spring already. Instead, it's better in this case to use this relation because we can figure out what the frequency is by observing this motion. Okay, so this is going to be our method in order to answer this question. So the relation between omega and K and M can be rearranged here to say that K is equal to M times the square of omega. Just square both sides, multiply by M. And so we know from the simulation that M is 250 grams or 0.25 kilograms. And we know also that omega is equal to 2 pi divided by the period. Okay. And so here's where we have to use the video. We need to actually somehow figure out the period. And conveniently, there's a clock here. And so why don't we just count how long it takes for a certain number of oscillations. So let me go back. Okay, so we'll go back to where the timer is. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so what I noticed, you see, it was difficult to figure out the period just for one oscillation. So what I did was count 10 oscillations, and I found that the period was about, it was like 15 seconds, maybe a little more for 10 oscillations. So it's more accurate to just count the total period for a larger number of oscillations. And that gave me around 1.5 seconds. So now we're in good shape because we can calculate that the frequency is 2 pi over 1.5 seconds. And then we can calculate that K is equal to m omega squared, so 0.25 kilograms, and then times 2 pi over 1.5 seconds squared. And that ends up giving us approximately 4 newtons per meter. It's a little bit larger than 4 newtons per meter. And so if we go back to our original question, then there it is. So this was one of the answers. So the answer for that one is C, that the spring constant is 4 newtons per meter. Okay, and that's pretty much it. I have this one extra question here. Might as well do it since we're here. So this is another one about velocity. And it's relating the graph of velocity versus time to the actual motion. And so we say for time equals 1.6 seconds, what does the actual physical system look like based on this velocity versus time graph? Okay, so let's have a look. 1.6 seconds. Apparently, the velocity is 0. Okay, so in our graph, this is going to be true. So if you think of up and down oscillating motion, oops, you can't see me. If you think of up and down oscillating motion, then the places where the velocity is 0 would be the bottom and the top of the oscillation. Okay, and so we can understand from the fact that velocity is 0 here that we're either at the bottom or we're at the top. And so then we want to figure out, is it answer A or is it answer C? So then we can look at, well, what happens at a slightly later time? So at a slightly later time than time equals 1.6 seconds, what we find is that the velocity is negative. And so that must mean that the velocity, that at time 1.6, we're at the top of the oscillation, okay? Because then after a little bit of time, we're going to start moving downward, so negative velocity. And so that would mean our answer is C in this case. Okay, and that is now all for today. So we'll see you on Wednesday.